This program is brought to you by Stanford University. Please visit us at stanford.edu.
Relativity. Relativity means special relativity, mostly, and then at the end, a little bit of general relativity, but general relativity done with some, not rigor so much as, well, conceptual rigor, if not mathematical rigor. Now, before I go ahead, let me just tell you one thing. I'm going to be gone for 2 weeks. I have to be in Israel. I have to give some lectures to the, I don't know, to somebody, some organization of philosophers. And so I will be gone for 2 weeks. That means, I think, does anybody have a calendar in their head? I'm coming back on the 24th, but I don't know what date that is. Yeah. But we will continue. We will get 10 full classes, even if we have to go into the into June a little bit. We'll get 10 full classes, but I will necessarily have to stagger them a bit. Yeah.
How about the lecture?
Oh, yes. That's also on Monday, isn't it?
Yes.
Yep.
So you're gone the next 2 weeks?
Yeah, I'll be gone for the next 2 weeks.
And then the one after that is the Monday.
Well, you know, if there's flexibility about the day of the week, we could just, when a thing like that happens, say, well, we will meet on Wednesday instead of on Monday or something like that. I know some people arrange their schedule one way or another, and it doesn't fit. But we will have one class before the Hofstadter lecture, and then we can decide what. I think so.
I think it's this.
No, I think there's another one. I think the 20. Oh, wait. Well, if nothing else, the Hofstadter lecture, I think, begins at 8. Oh, there's a problem there. I may have to be available. Well, one way or another. I'll be gone the next 2 Mondays, and then I'll be back. Let's assume we will meet here on the Monday after I get back.
That's the 30th. That's the Hofstadter lecture.
That's the 30th. That's the Hofstadter lecture. I will be here. Okay. Now, I am also the host for the Hofstadter lecture, so this is gonna. So you know what it'll probably mean is we'll go to the Hofstadter lecture, but I won't. I'm not going to count that as a regular class if we do that. And we'll see, at that time, we'll see if we can figure out a time to, some way to make adjustments.
Just make, one suggestion on that is that in the past, when that kind of conflict came, you just maybe start a class at 6 instead of 7.
We never did that, did we?
Yeah, we did.
Did we?
Yeah,
we can do that. Oh, you mean specifically for the? Yeah, we could do that. Okay. Good. Let's do that. Yeah. All right. So let's assume that on the week after I return, that we meet here. The Monday after we return, we meet here at 6. Does that work for everybody? Okay. Good.
The 30th?
I think it's the 30th. Yeah. But then I would like to find maybe some ways of. I'm always in the situation where I have to be someplace else. I have to be 2 places at the same time, and it's hard to do. So if we can somehow juggle times, that does help me. Yeah. Yeah, I'm more than a little uncertain most of the time. All right.
When you were talking about the next term, you gave me a summer or?
No. Summer, I won't teach.
You're somewhere else.
No, I'm actually usually here, but no. I need to stop and do nothing for the summer. I need to think about things. All right, let's begin with special relativity, and let's really do the mathematics of special relativity carefully. Let's work it out. Work out the details of energy, momentum. Well, first we're going to work out the details of space and time and space-time. The details and the symmetries, Lorentz transformations, what it means for things to be synchronous and so forth, to work these things out with some care and some precision. And then move on to, we could call that kinematics. Kinematics, space and time, how things move, but not why they move. Then comes the question why things move, and why things move is because of forces. And forces, of course, are the subject of dynamics. And so we will study a little bit about the dynamics of special relativity. Energy, momentum, force, the analog of Newton's equations, not Newton's gravitational equations, but Newton's equations of motion for special relativity. E equals mc squared and all that stuff, what it means. And I think that should probably take us about 5 lectures, 5 or 6 or something like that. Then I would move on to some general relativity. The general relativity that we'll do will not be incorrect. It will be absolutely correct. But what I will teach less of is the Einstein field equations and more of what happens to particles and objects when they're in a given gravitational field. All right, so what is a gravitational field, curvature of space-time, and that kind of thing, without trying to get into the harder, much more difficult subject of solving Einstein's field equations. That's hard. It's hard for me, anyway. So that's what we'll do this quarter. Basic relativity, special, and a bit of general. We'll probably get to the point where we can talk about black holes a little bit. Maybe also get to the point where we can talk about expansion of the universe. Some of the interesting things that flow out of the general theory of relativity. All right, now let's begin. First of all, what do we mean by relativity? Well, what do we mean by relativity in general? What we mean by relativity is the idea that, of course, all of you know, that the laws of physics are independent of the frame of reference in which you study them. The frame of reference, simply for our purposes here, means a state of motion of a set of coordinates. If you like, the way to think about it is to imagine space being filled up with a lattice, an imaginary lattice of meter sticks, so that every point in space is labeled by a x, a y, and a z, a set of meter sticks, and at each vertex of the lattice, a clock. And the clock measures time. Now, in Newtonian physics, Newton imagined that time was very, very universal. He imagined God's time. God's time was the same for everybody. There was no question of what the time was on a particular clock. Clocks were synchronized. It didn't matter how they moved. It didn't matter how you move. It didn't matter how you move with your watch or without your watch. Everybody would agree at every instant, at every place in the world on what the time is, t. That, of course, had to be given up when Einstein moved to special relativity. But the idea of relativity was already there before Einstein, long before Einstein. It basically goes back to Galileo. So let me just remind you what Galilean relativity is, how and why it failed. The way I like to think about relativity is I like to imagine, I always like to have a picture in my head that I can think about intuitively. And the picture that I have in my head is the same one that Einstein thought about. Moving along in a railroad train in a railroad which is extremely well made. So well made that the tracks are perfectly smooth. So smooth that the train doesn't rattle, it doesn't shake, and it just moves with absolute uniform velocity. Now, what are the laws of physics? Well, my favorite description of the laws of physics in this train is what I like to imagine the laws of juggling. Juggling is good physics, incidentally. To be a good juggler, you have to have a very, very good sense of timing. You have to have a good sense of gravity. You have to have a good sense of a lot of different aspects of physics. Of course, you may not consciously be using those, but at least unconsciously, all kinds of physics comes into juggling. So there are some rules. You throw the ball up, and you wait a certain amount of time, and you catch it, and you transfer it, and you do whatever it is that you're supposed to do, and you call all of those the laws of physics or the laws of juggling. Now, it's a fact of nature that in this train, which is moving with absolute uniform velocity relative to a stalled train, a train that happens to be at rest on the surface of the Earth, for example. Imagine the surface of the Earth. One train moving, one train standing still. The laws of juggling are exactly the same. This, in fact, before Galileo, this was something of a surprise. In fact, not a surprise. People didn't understand that. They actually imagined, of course, they didn't have trains to think about. But if you would have told them about trains and moving along with a train, the average scientist probably would have thought that when you throw a ball in the air in the train, you probably have to compensate for the motion of the train by, if the train is moving that way, you probably have to move your arm over to the right in order to catch the ball, because the train moving will lead to moving out from under the thrown ball. Of course, this is wrong. The laws of juggling are the same in the stationary train and the moving train, identical, exactly the same. And that was something that Galileo realized. Galileo was the first to realize it, and Newton spelled it out in great detail in his laws of motion. So let's begin with Galilean relativity. Like all theories of relativity, it's a theory of transformations. Transformations of coordinates and transformations of phenomena from one frame of reference to another. Again, a frame of reference means, as I said, a lattice of meter sticks with clocks which have been synchronized, and we'll have to discuss what we mean by synchronized, but clocks which have been synchronized at each corner of the lattice. And now we can imagine having two such lattices. One is moving relative to the other. One is moving relative to the other. In each frame of reference, the clocks have been synchronized in the appropriate way, and so we have to transform information from one frame of reference to another. Various kinds of information. What is the energy of an object? What is the temperature of an object? I don't know, any number of different kinds of quantities. We could ask, if you know it in one frame of reference, what is it in the other frame of reference? Now, the simplest set of quantities has to do with location. Location in space and location in time. The things which are recorded by the meter sticks and the clocks. Right? So how do we transform from one frame of reference to another? Here we have a frame of reference. Let's first of all draw a frame of reference. The first thing to do when you start a relativity problem is to draw a picture. And the picture is a picture of space-time. Time vertically, as always, and space horizontally. And at least in the beginning, we're mainly going to be interested in problems involving motion along one particular axis. So let's call it the x-axis. The y and z directions, for the moment, will be rather passive. They won't play any great role for a while. They'll come into things. And so every point in space and time, or every point on the blackboard, stands for a place in space and a time in time. So it's called space-time, naturally enough. Okay. Now if I wanted to draw the meter sticks, let's just imagine drawing the meter sticks. Here's the origin right here. Time equals 0 here. The clocks have been all adjusted. So the time is equal to 0 all along the horizontal axis. And as we flow up, the clocks tick off time, seconds, years, whatever it happens to be. All right, now, if we move down the line a little bit, we come to the end of the first meter stick. So here's the end of the first meter stick. Its trajectory is a trajectory in space-time. The second meter stick is over here. The third meter stick is over here. And the sequence of meter sticks laid out along the horizontal axis, as time goes on, define a series of stripes like this, which represents locations in space, if you like. This is x equals 0, x equals 1. Needless to say, we can also go backward to x equals -1, x equals -2, and so forth. There's no reason to stop at x equals 0. X equals 1, x equals 2, x equals 3, x equals 4, and so forth. Now, the clocks tick. And so a clock which reads, there is no time that we call 0, is there? We never hear of talking about time 0. I mean, you know, an ordinary clock. Time 0 is usually what we call 12 midnight, I guess. All right. But anyway, let's use the term time t equals 0. T equals 0 is over here. T equals 1. 1 what? 1 second or whatever. 2 seconds, 3 seconds, 4 seconds, 5 seconds. And now if we draw some horizontal lines, those represent lines of constant time. So the whole world, space and time, becomes a lattice. Not a real lattice, an imaginary lattice. And you can make that lattice as fine as you like. It doesn't have to be meters, it could be centimeters or microns or Planck lengths, or if smaller than that makes any sense, we can make it as fine as we like. And in that way, every point in space-time represents a precise time and a precise place according to this lattice. All right, now that's your reference frame. You are the people in the station or in the broke-down train which isn't moving. All right, you're sitting there waiting at rest at the surface of the Earth. But my train is moving, and my train is moving with velocity v. All right, I'm in the caboose of the train at the tail end, and let's say at time t equals 0, the caboose is right over here. But as time moves on, as time moves ahead, my train moves forward. I'll assume it moves forward. It could also move backward. And so the tail end of the caboose looks like that. The next car might look like this. I'm imagining now cars 1 meter long. And so my series of constant position coordinates are tilted relative to yours in a space-time plot like this. All right, now we're not up to Einstein yet. We're doing Galileo and Newton. Galileo and Newton could ask the question, if you people in the station give a certain set of coordinates, let's say x and t, to an event. Here's an event right over here. An event means a point of space-time. If you label the point of space-time x and t in what we'll call the stationary reference frame, what are the coordinates that I assign to it in my moving reference frame? Well, if Galileo were here, he would look at this and say, look, time is time. I believe, like Newton will believe in a few years, that time is universal. Everybody agrees about time. And in fact, he could sort of check that. There weren't very good watches at that time, but he could check it with a pendulum or something like that. And he could take the pendulum, and if he was careful, he could put the pendulum on a moving train. There were no trains, there were no watches, but he could imagine taking his pendulum and moving it along and bringing it back and checking it against the pendulum at rest. And if he did it well and he did it carefully, he would find that the two pendulums agreed. The way the pendulums move would not in any way influence how rapidly they tick off. And of course that's true for the pendulums until the pendulums start moving too fast. Right? So Galileo, first of all, would have said T prime, that's the time in my frame of reference, the moving reference frame, is the same as your time. But my coordinate, x prime, what does my coordinate mean? Let's take this point over here. The coordinate, the x coordinate that I assign to this point over here, is the distance not to your origin of coordinates, not to your origin of space, but to my origin of space. My origin of space is over here. Okay? So I will assign a smaller x. X prime will be smaller than x, and what it will be x, your x, minus the amount that you move, or sorry, the amount that I move in time t, and that's going to be minus the velocity times t. So t prime equals t, x prime is equal to x minus vt, where v is the relative velocity of the two frames of reference. Okay. We can go back and forth. We could solve this equation. This gives me the primed coordinates in terms of the unprimed. I could solve this and rewrite it as t equals t prime, x equals x prime plus v. Now I would, if I just use the second equation, I would write plus vt, but since t is the same as t prime, I'll just write vt prime here. The top equation would be how the moving, would be how the stationary observer converts his information into the information of a moving observer, and the inverse equation would be how you go back. Okay? This is the basic mathematics of Galilean relativity. Okay? Let's check some things. First of all, what kind of things are invariant? The idea of invariance is very important. The idea of invariant, or an invariant, invariant is both an adjective and a noun. Equations can be invariant. An invariant means a thing which everybody agrees about, a quantity that everybody agrees about. All right, so let me give you an example of a quantity that everybody agrees about. Everybody meaning these two observers or any other ones that we also throw in. Yeah, question?
You were saying about the pendulum, how you can check
Yes.
that you can take the pendulum
Well, I was
and return
yeah,
and come back.
yeah.
How does he know that when he moves the pendulum away, that he's speeding it up and then it's kind of he's decelerating to bring it back? How does he know that?
Of course, the answer is he doesn't. But if you do it with an ordinary watch, with a good, no, I mean, how Galileo would have known it, I think Galileo just guessed it. How you would do it is you would take your high-quality Rolex watch and you would just go and do it. One person would stay in his seat and the other person would march around the room a few hundred times and then come back and check their watches. Now, the answer, of course, that we know, because of hindsight and because we're living in the 21st century and Einstein was 100 years ago, is there will be a tiny discrepancy. But that discrepancy is so small that for ordinary purposes, for ordinary daily experience, we would simply say the rate at which clocks tick off time doesn't depend on their motion. And that's an experimental fact. Experimental fact in the sense that, that if we actually did it with ordinary clocks, it would work. It would work to very high precision. Of course, at some level, it fails. But that's what special relativity is about.
I guess ignoring the special relativity thing, I guess I have a problem that you're bringing the clock back to the same spot.
Yeah.
And minusing whatever.
Oh, you think it might have sped up as you went one way and...
Come back, it slowed down.
Yeah, well, that might have happened. That would mean that there was basically a difference between left motion and right motion. So we could try the same experiment going the other way. Well, maybe the same thing would happen, but then if east and west, we would try it north and south. We might also take my watch and go around you in circles for a long period of time and do all kinds of experiments.
Or just go
with
one direction and use a telescope.
use all kinds of ways. We would try all sorts of obvious things, and they all work. Right? You don't need a telescope. Use a telephone to communicate the information back and forth. Send light signals back and forth to check our watches, and so forth, and it would work very well. It would work very well until we start to move too fast. Okay, then it breaks down. All right, but the point is that the Galilean relativity was based on a guess. It was frankly based on a guess, and the mathematical translation of the guess is these equations. All right. Now, there are some obvious invariants. For example, here's something that's invariant. At an instant of time, look at the distance between two events which are synchronous or simultaneous. Simultaneous being used to mean at the same time. Take two events at the same time. The distance between them will be invariant. Why is that? Let's take the two events. Let's call them x1 at time t1 and x2 also at the same time t. Let's not even bother labeling the time. At the same time. These are two events at the same time, and the distance between them is simply x2 minus x1, and that we can call distance. All right. What about the primed coordinates? The primed coordinates are x prime 1 is equal to x1 minus vt, x prime 2 is x2 minus vt. Notice that the actual coordinates are not invariant. They don't assign the same values of x, but they do assign the same values if we now subtract these two, or subtract them, the top one from the bottom one, then x prime 2 minus x prime 1 is equal to x2 minus x1, and then the vt's cancel. So the separation between 2 points at the same instant of time, I emphasize at the same instant of time, because it wouldn't be true if we did it at different instants of time. Yeah?
The t's on the right
Yeah.
are not the same as the t's on the left.
Yeah, they are. With an event at x1t and another event at x2t. This is t over here.
Right. Okay, got it.
Got it, okay? This is t, here's x2, here's x1. Right? The separation between the 2 points is an invariant. That's the language we would use. Let's imagine that we have a particle trajectory. A particle trajectory means an x of t. X as a function of t would be a trajectory of some particle. I'll put it over here. Trajectory of some particle is an x at each function of time. First of all, is the position invariant? No. X and x prime are not the same thing, but we can write x prime of t is equal to x of t minus vt. All right, so if I know the trajectory x of t, not v of t, but v times t, if I know the trajectory of a particle, or if you know the trajectory of a particle x of t, you can communicate it to me, and the communication will be in the form of telling me what x prime of t is. What I will see is an x prime of t, which will be your x of t minus vt. All right, so the coordinate of the particle itself is not invariant. What about the velocity? The velocity is just the time derivative of the position. All right, so the velocity, which would just be, let's call it dx prime by dt, that's equal to dx by dt minus v. So no, velocities are not invariant. What you see as the velocity, I see the velocity being diminished. V could, of course, be negative. I mean, there's nothing intrinsic about the sign of v. But I see a velocity which is shifted by amount v. That's obvious, of course. I'm moving along. You shoot an arrow. I see the arrow going slower than you see the arrow going for obvious reasons. What about acceleration? So, first of all, position and velocity are not relativistic invariants in Galileo's theory of relativity. But let's differentiate again to get the acceleration. D second x prime, well, let's see, by, let's put it here, d second x prime by dt squared, that's the acceleration that I see, is equal to the acceleration that you see minus the time derivative of v. But v is a constant. I am assuming that the relative velocity between the two frames of reference is constant. That's equivalent to saying that these tilted lines are straight lines. So the acceleration, the difference v doesn't make any difference. The time derivative of a constant is 0. And so acceleration is an invariant. The acceleration that I see of an object, I mean, not my acceleration, I'm not accelerating. I'm in the caboose of the train, I'm moving along with uniform velocity, but I see objects moving back and forth in front of me, moving to the left, moving to the right. Sometimes they accelerate. You see the same objects, you also see them accelerate, and we will agree about the acceleration. So acceleration is an invariant. Now, I'm not sure which is cause and effect here, really, but let's say it this way. The fact that acceleration is itself an invariant is a strong suggestion that the laws of physics should be in terms of acceleration, not velocity, not position, that the law of physics, the laws of motion, if they are to be invariant, the laws of physics should involve acceleration, since we all agree on the acceleration. Well, of course, that's exactly what F equals ma says. Force is equal to mass times acceleration. Acceleration, we all agree about acceleration. Well, let's analyze this a little more closely. Supposing we're talking about two objects which exert forces on each other, and for the moment everything is taking place along the x-axis. We usually imagine, correctly for most cases, that the force between two objects only depends on the distance between them. All right? Only depends on the distance between them. The force between two objects, gravitational force, electrostatic force, only depends on the distance between them. The coordinates of the particles themselves are not invariant, but the distance between them is invariant. That's what well, where did we write it? Up on the top here. Everybody agrees about the distance. So the distance is an invariant. And if the force only depends on the distance, it says that the force between two objects is an invariant, meaning to say that everybody agrees about it. So if you, in your frame, were to measure the force between these two objects, which are moving somehow, and I, in my frame, whizzing by it, measure the force, according to Newton and Galileo and everybody who came after them up to Einstein, force is an invariant because the distance between two objects is invariant. That leaves only one more symbol in this equation, mass. In order for Newton's theory to make any sense, it was necessary that mass is an invariant. If all the terms in the equation are invariant, then so must be the mass. And so according to Newton, every object has a mass, and everybody agrees about that mass. There's no discrepancy because an object is moving about a 1 kilogram object is a 1 kilogram object is a 1 kilogram object, even if it's moving past you on a railroad train. So Newton's law of motion is invariant. Here's the language. Newton's law of motion is invariant under Galilean coordinate transformations. There's a Galilean coordinate transformation, and Newton's laws of motion are invariant under it. The idea of relativity is that all the laws of nature, whatever they happen to be, are invariant under the appropriate analog of the Galilean transformation. Now, the problem is that that clashed with electromagnetism. At the moment, we haven't learned anything about electromagnetism, but you all know that electromagnetic waves are called light, and that light moves with a certain velocity. Maxwell's equations predict what that velocity is, and if you think of Maxwell's equations as laws of physics that everybody should agree on, then the speed of light must be the same for everybody. That's really all there was to it. Einstein really used no more than that. Of course, he was guessing. He was guessing that Maxwell's equations were the same in every reference frame. In other words, he was guessing that Maxwell's equations, which were laws of nature, which were so compelling that they would have to be the same in every reference frame. And that, of course, led to a big problem. It led to the problem of the speed of light, that if Maxwell's equations are the same in all reference frames, then the speed of light is the same in all reference frames. But how can the speed of light be the same in all reference frames if one frame is moving relative to the other? We could work it out. We could work it out using Galilean relativity. Let's take a light ray. A light ray, a little blip of a light ray moving along. It moves along with x equals c times t. That's what, where c is the speed of light. Okay? That's what Maxwell's equations said. Well, Galileo would then have had to say, let's ask how that light ray appears to move from the point of view of the moving reference frame. And that will be x prime, which is equal to x minus vt. So far, this is just the Galilean representation of the transformation. That is equal to ct, x is equal to ct minus vt. And he would have just said, well, that's the same thing as saying c minus v t. So Galileo would have had no choice but to say in the moving reference frame, the speed of light differs from the speed of light in the stationary reference frame by the relative velocity. Okay. That, of course, made good intuitive sense. It is the way sound would work. It is the way water waves would work. If water waves move, what's a typical velocity of a water wave? I don't know, a couple of meters a second or something like that. How much?
A few for small ones.
Yeah. Meters per second. Let's say 1 meter per second. But I'm flying over at a half a meter per second. I'm flying over the wave. Then I see the wave moving at a half a meter per second. So it's completely unreasonable to expect that water waves have a universal velocity that all observers see. Now, most physicists, of course, at the turn of or at the end of the 19th century, simply came to the conclusion that, well, in the 1850s, 1860s, when Maxwell was active, simply came to the conclusion that some frames of reference are better than other frames of reference, that there is no relativity, that there exists a frame of reference, God's frame of reference. Don't tell the ombudsman I said that. Or do tell the ombudsman. God's frame of reference where Maxwell's equations are correct. In other frames of reference, Maxwell's equations must be somewhat different because in other frames of reference, obviously light moves with a different velocity. And so, as you well know, various physicists tried to study the dependence of the velocity of light on the state of motion of an observer, and systematically they found no dependence. We won't go through the various experiments. Several different kinds of experiments to try to detect the fact that a moving observer would see a speed of light which would depend on the state of motion, and as you know, no such effect was ever discovered. The result being that physicists had no choice but to go and review the basic ideas that went into this definition. Now, Einstein himself claimed he never even knew about the experiments. I'm inclined to believe him. I mean, you know, they didn't call Einstein Einstein for nothing. I mean, so I think we give him credit. He said when he was 16 years old, he thought about moving along with a light wave. The light wave didn't oscillate, didn't move, didn't do anything, just looked frozen. And he somehow knew enough to know that Maxwell's equations were inconsistent with that. And his choice was to believe that Maxwell's equations were basic laws of nature. Basic laws of nature which should be the same in every reference frame. So, something was wrong, and he had to go back to some very, very first principles. In fact, the very first principles which this lattice represents. The idea of coordinates, the idea of times, the distinct times and so forth, and went back and said, let me begin all over again with one assumption, well, two assumptions. The first assumption is the principle of relativity, namely that in every frame of reference the laws of physics are identical. The second assumption is that in every frame of reference the speed of light is always the same. Let me take those as postulates and see what I can derive. The first thing he derived was something that is implicit in this diagram, which I partly spelled out, partly didn't spell out, but let me spell it out now, that if two events are simultaneous, as seen in one reference frame, they will be simultaneous in every reference frame. It's exactly the statement that t prime equals t. If two events occur at the same time in one reference frame, they occur at the same time in any reference frame. Einstein realized very quickly that he could not maintain that. And here's roughly the way he thought about it. He said, let's go way back to the beginning and even start with the whole idea of synchronizing clocks. We can lay out our meter sticks. It's clear enough what we can do. We can lay out our meter sticks. All right? We lay out our meter sticks on the ground. But now you have your clock, you have your clock, you have your clock, you have your clock over there. And you want to synchronize your clocks. Make sure they all read the same at the same instant of time. What does that mean? Well, there's various ways you could try to check whether your clocks were synchronized. But Einstein decided to use light. He wanted to use light for the obvious reason that his basic postulate was about light. So he wanted to use light to synchronize clocks. So here's the way he synchronized clocks. He said, let's see, put somebody in the middle. Now, what does the middle mean? Let's take you and you. You're the two endpoints. What does it mean to say somebody in the middle? Well, you can measure with meter sticks the person in the middle and adjust with the meter sticks until that person in the middle is exactly halfway between you. Now, at exactly noon, you're going to emit a flash bulb. You're going to light up a flash bulb, and the light signal is going to go, well, it can go out all around you, but in particular, it's going to go from your position out in that direction. You'll do exactly the same thing. When your clock is also at time t equals 0, t equals 0, did I say 0 or noon? Whatever. At noon, you will also send out a flash signal. If the person who is in the middle sees the flashes simultaneously, in other words, if the left flash and the right flash go right by him simultaneously, then we will agree that your clocks are synchronized. If he sees your flash before your flash, then he says you better readjust your clock a little bit, go back, try it again, set your clock back a little bit, and keep doing it until the person in the middle sees the flashes of light instantaneously the same. Now, everybody in the room does the same thing with respect to everybody else until everybody's clocks are synchronized by exactly the same definition. That somebody halfway between them will see flashes of light emitted at the same time, will see those flashes of light at the same time. Okay, then Einstein realized there's a problem. That much is okay. That much is okay. We can synchronize all of your clocks. But now, what about me moving past you? Or, let's have me moving past you. And let's see how this should work. I have my coordinate frame laid out. And I move past you. I look at your light ray. But because I'm moving, by the time your light ray gets to me, it has had to go further than your light ray did. So it's quite obvious that I'm going to see your light ray before I see your light ray, even if you emitted them at exactly the same time. Even if you emitted them at exactly the same time, according to all of your reckoning, I, who happen to be moving this way, will reckon your light ray as being emitted later, because I see it later, because it has a greater distance to go. So Einstein realized that the idea of simultaneity was a relative idea, that if everybody synchronizes their clocks by the means of light, there will be a discrepancy in what, in different frames of reference, is counted as simultaneous. Well, I want to work that out. I want to work that out in detail, just using light. How does simultaneity break down? Another way to ask it is if these 2 points are counted in the stationary reference frame as having the same time, which 2 points in the moving reference frame will be said to have exactly the same time? That's something I want to work out next. We'll take 5 minutes and work that out in detail, and that'll give us the Lorentz transformations. Lorentz transformations which implicitly have in them that simultaneity is a relative concept. So that will be our next challenge, to replace this equation by one that's consistent with the idea that light travels with the same velocity in all frames.
What if I synchronize the clocks using sound waves?
Using what?
Sound waves. Suppose I just yell it. I have 2 people yell.
Then you will find that the law that says that the speed of sound is, what is it, about 1,000 feet per second? That's not a law at all, and that moving observers do detect different velocities of sound. If you do it at rest, in a frame of reference where the air is at rest, that's a perfectly good way to synchronize, clocks. But then somebody moving, you'll do all these things, and you'll discover in the end that it's not consistent to say that the speed of sound is the same in every reference frame. what we're going to be using, we're going to use the idea that light is the same. There's nothing wrong with synchronizing clocks that way. Nothing at all. You wouldn't want to do it, though. You wouldn't want to synchronize clocks on a moving train if the train was an open-air train and you get the point. If it was an open-air train and the atmosphere was at rest and you were moving through the atmosphere, that would be a bad way to synchronize your clocks.
This would be like having ether.
Yeah, exactly. So Einstein said he doesn't care. E is going to simply assume the speed of light is the same and see where it takes him, see where it leads. Does it lead to something consistent? All right, so as I said, his first observation was there's something wrong with the idea that simultaneity is universal, or that the simultaneity of two events is an invariant. So here's how he began. I actually don't know how he began. This is the way I begin. It's been too long since I've read his paper. Again, we begin with a drawing. And now we have this is the rest frame, and we have 2 points laid out a distance L apart. This distance is L, and this distance is L. L stands for length now. It could be 1 meter, but let's keep it general. Distance L is measured off, another distance L is measured off, and here are the trajectories of the points which correspond to being L units apart. Okay? This could be your seat, and that could be your seat. And the one in the middle, since it's equally distant between the two of them, is the person who happens to be vacant but is sitting in the middle between the two of you. Okay, so that's the first setup now. Now, if the clocks are synchronized, what does that mean exactly? It means that if at time t equals 0, both observers at the two ends here send out a light signal, the light signals will intersect at the same place, like this. Oops, I missed. That a light signal from this side, if it's sent out at the same instant, in other words, synchronous, in this frame of reference, with a light signal that's sent out from this instant, that the 2 light signals will cross the intermediate observer here at exactly the same time. Now, light moves, of course, very fast. That means that this drawing is a bit, well, that's a little funny, because light moving so fast, it would mean that light rays are practically horizontal. They move an enormous distance in a short amount of time. But we can fix that. We can fix that by working in units in which the speed of light is equal to 1. Let's do that. Later on, we'll put back the speed of light, but for the moment, let's set the speed of light equal to 1. How do you do that? You work in units of space, which are adjusted the right way so that in 1 second of time, light goes 1 unit of distance. A light second. Or years and light years, or whatever you like. And so the vertical axis and the horizontal axis here are measured in units in which the speed of light is equal to 1. If the speed of light is equal to 1, then a light ray satisfies x equals t, not ct, but just t, and that would be a 45-degree line. That's a light ray moving to the right. A light ray moving to the right satisfies, a light ray moving to the right from the origin over here satisfies x equals t. What if it's a light ray moving to the right from some other position? Well, then it satisfies x equals t plus some constant, namely the offset. So if it's a light ray, any light ray moving to the right satisfies x equal t plus something.
C equals what?
D. Thank you. D. And what about a light ray moving to the left? That's x equals minus t, or minus t plus some other constant, plus d prime, I don't know. So these are the motions of light rays, and they correspond to 45-degree angles. 45-degree angles, a slope of 1. A slope of 1 corresponds to a velocity of the speed of light. Things moving slower than the speed of light move more toward the vertical. If it made sense to think about things moving faster than the speed of light, which it doesn't, they would be moving on trajectories which were more horizontal. So these two clocks are synchronized because if at the same instant of time, or another way of saying it, is these 2 points here must be at the same instant of time in this reference frame, in the stationary reference frame, because the light rays will intersect the intermediate observer here right at the same instant of time. Now let's draw in a second observer. A second observer, in other words, a second reference frame, and the second reference frame is moving. It's supposed to be a straight line, and it's moving with a motion x equals vt. V is now the velocity of the moving observer, and this curve here is now x equals vt. From your perspective, I'm moving along with velocity v. So you watch me, and you say at each instant of time, my position moves, and it moves with a velocity v. This is incidentally the definition of velocity. This is the definition of the velocity that you see me move with. Okay? So this is moving along like here. Let's draw in some more lines. Here's a second. I want to draw this good and parallel to the first. Does that look parallel? Close enough. This one's also pretty parallel, like that. Okay. What do we want to do next? Okay. Now let's look at the moving frame of reference. Again, this guy is halfway between these two. Right? He started out over here halfway between these two. They're moving with uniform velocity. He stays halfway between these two. But notice that at his location, the two light rays do not arrive at his position at the same time. At his location, one of the light rays arrives much later than the other one. So according to this moving observer, he must conclude that these 2 points were not synchronous. The light rays emitted from here and here could not have been synchronous from his point of view, because from his point of view, they should have arrived at the intermediate position at the same time. In fact, he can reverse the logic. He can say, where along this light ray does it correspond? Let's see, how to say this right. Yeah. Let's forget this light ray for a minute. And let's follow this one until it actually hits the observer. This is the person in the middle. Where would a light ray have to come from along this trajectory in order that the guy in the middle here would conclude that the two light rays were emitted simultaneously? It's easy. Just trace a backward light ray, also at 45 degrees, to that point. Trace a light ray backward along 45 degrees to a point over here. And now in the moving frame of reference, if a light ray is emitted over here, and a light ray is emitted over here. This is a bit of an exaggeration. I think this line is too shallow. Let's maybe go back a little more. Hit exactly the same place.
Well, that's because the other one's not really quite far.
Yeah. If a light ray were emitted from here to the left, and a light ray were emitted from here to the right, they would hit the central observer over here at exactly the same time. So the moving observer will conclude that this point and this point are synchronous, whereas the stationary observer concludes that this point and this point are synchronous. It's obvious from the beginning that the idea of synchronous cannot be the same in the two frames. But can we do it quantitatively? Can we really figure out quantitatively exactly where this point lies? And can we figure out all the points that the moving observer will call synchronous with the origin over here? And that's not too hard. It just requires a little bit of simple algebra. So a little bit of geometry and algebra. Let's work it out. The first thing to do is to make some simple equations for all the lines that are drawn here. All right? We need some simple, we want to be quantitative. I want to write some equations for the various lines. This line is x equal vt. What is this line over here? This line is x, let's write it in, x equals vt plus L. Why? Because it's shifted over by distance L. Right? So for its x is Vt plus L. This is x means from the stationary reference frame. The stationary reference frame sees the black lines shifted up by distance L. So it's x equals Vt plus L. What about this one? Vt plus 2L. That's x equals Vt plus 2L. We want to locate this point. The object is to locate this point right over here. Why? Because it's the one that the moving observer says is synchronous with the origin. So we'd like to find out where it is. What's the equation for this line? X equals t. That equation is x equals t. Let's first locate this point. This point is at the intersection of two lines that we know. One of them is x equals t, and the other is x equals vt plus L. Let's write those two equations and find out where those two lines intersect. So one of them is just x equals t, and the other one is x equals vt plus L. All right, that's easy. Wherever you see x, put t, and we get t equals vt plus L, or 1 minus v times t equals L. One more step. T equals L divided by 1 minus v. Do I have that right? Let's check it. Yes. That's this point right over here. It occurs in the rest frame at a time which is v, which is L divided by 1 minus v. What about x? What about the x of that point? It's equal to t. All along this line, it's the same thing. X equals L over 1 minus v. That's this point over here. Let's call it point capital A. This is point capital A. Now that we know where point capital A is, let's see if we can trace a line backward until it hits here and figure out where this point is. That's our goal, to find out where this point is. All right, what about this line? What do we know about this line? We know about this line that it's a backward-going light ray. So it's of the form x minus t is equal to a constant. Oh, sorry, x equals minus t plus a constant. The backward-going light ray is x equals minus t plus something. Let me just give that something. I don't want to call it d prime. I'm going to call it b. Or another way to write it is that x plus t equals b. We don't know what b is yet. How am I going to find b? This is x plus t equals b. How will I find b? Anybody got an idea?
Yeah, it's the same, it's twice x from point A.
Right. Right. What we do is we use the fact that this line goes through this point. Right? This line goes through this point. At this point, x and t are equal. And what are they equal to? They're equal to L over 1 minus v. So at this point over here, x plus t is just twice L divided by 1 minus v, and that's equal to b. So we found b. We found out what this b is that goes into this equation for this backward moving light ray over here. All right, let's write it down. X plus t is equal to 2L divided by 1 minus v. So now I know this line, but I want to find its intersection with this one. So I'll write right underneath this equation, I'll write the equation for this line. That's x equals vt plus 2L. All right, I now have two equations that tell me where the intersection point is. Let's see, shall we solve them? A little bit of a nuisance to solve them, but let's do it. Okay, no, it's not hard at all. Let's subtract the two equations. That will get rid of x for us. If I subtract the two equations, that will get rid of x. That'll give me on the left here t, and on the right-hand side I will have equals 2L over 1 minus v minus, looks like, am I doing this right? Minus vt minus 2L? Oh, no, plus 2L. No, minus 2L. Minus 2L. All right, let's move all the t stuff over to the left. That gives us t times 1 minus v equals 1 plus v equals 2L. Both these terms have 2L in them. And then one of them has 1 over 1 minus v, and the other one just has minus 1. All right. 2L is common to both of them. It's out here. And it's just it's just 1 over 1 minus v minus 1. Okay, what's 1 over 1 minus v minus 1? It's just v over 1. Just v over 1 minus v?
Yeah.
Right. Yeah. 1 over 1 minus v minus 1 minus v over 1 minus v is 1 minus 1 cancels. V over 1 minus v, right? V over 1 minus v. And finally, I have now located what t is. T is 2L times v divided by 1 minus v times 1 plus v. 1 minus v times 1 plus v is just 1 minus v squared. So, first of all, I found t is equal to 2L v over 1 minus v squared. That's the time of this point over here, t. What about its x? Well, that's easy to find. We can find it from two ways. We can either find it by plugging into this line or by plugging into this line. Which one is simpler? Let's see. It looks to me like it's easier to plug into this one. Okay, so let's plug into this one. That says that x is equal to 2L divided by 1 minus v minus t. minus 2LV over 1 minus V squared. Anybody do that in their head?
No, you get
No.
2LV.
plus 2LV and 2LV's cancel out.
I think we better do it. We better multiply top and bottom by 1 plus V so that we have the same denominator. So let's multiply by 1 plus, well, let's do it separately. 2L times 1 plus V divided by 1 minus V squared minus 2LV. It looks like to me like it's just 2L divided by 1 minus V squared. All right? So it's X equals 2L over 1 minus V squared. Now, I'm actually not so interested in either T or X. What I'm interested in is the slope of this line. I'm interested in the slope of this line, which is the ratio of T to X. I'm actually interested in what this line is. I'm interested in this curve here. This curve has the form X equals something times T, but we can read off what it is now. It's just a ratio of X to T. What's the ratio of X to T? The ratio of X to T is just V. Is just V. So this curve is T equals Vx. Let's check that. T equals Vx. Yes, T has an extra factor of V in it from X. T equals V times X. Well, that's kind of interesting. We did this whole big construction, and what we found out is that what the moving observer calls synchronous, the stationary observer calls T equals Vx. We can erase everything else. Let's just keep track. Here's the moving observer. He moves with X equals Vt. That's his time axis. X equals Vt. But the x-axis is T equals Vx. Okay? All these points along here are at the same position from the point of view of the moving observer. All these points along here are at the same time from the point of view of the moving observer. All these points are synchronous from the moving observer's point of view, not from the stationary point of view. And look, one of them says X equals Vt, the other says T equals Vx. Very symmetrically related to each other. Very symmetrically related. Let's just abstract from the whole thing now what we've learned, because we've set C equal to 1. Okay? So let's actually put some units into it. Let's get the units right. When you do a thing like you set C equal to 1, then of course lengths and times have exactly the same units, and velocities are dimensionless. The velocity is the ratio of a length to a time. If C is 1, velocities are dimensionless. But let's try to get some dimensions back into it and restore some correct dimensions to it. All we have to do is multiply by the appropriate powers of the speed of light in order to get the dimensions to be consistent. This is already consistent. X is equal to a velocity, which is a length over time, times a time. But this one does not look consistent. What do we have to do to it to make it consistent? The answer is, I think, divide it by the square of the speed of light. When the speed of light is set equal to 1, this curve is T equals Vx. There's a unique way to restore the C's so that you get the same answer when C is equal to 1, but so that dimensions are restored. Let's check the dimensions. This is a time. We have a time equals. Now, a velocity is a length over a time. An x is a length. And in the denominator, we have a length squared over a time squared. So let's see. That is in fact dimensionally correct. Yeah. A c in the denominator, a c squared in the denominator restores the dimensions. So if we include the speed of light, that would be the formula. In fact, including the speed of light, you see something interesting. you see that when the speed of light is very, very large, the slope of this line is very, very small. T equals v times x divided by an enormously big number. Right? Speed of light squared in metric units is 10 to the 17th or something. So this is an enormously big number downstairs. And that says that this is a very, very shallow line. So shallow that for most practical purposes, simultaneity really is the same in all reference frames. But when things are moving with anything like the speed of light, we have to account for these discrepancies. And so, but if we set the speed of light equal to 1, then the diagram has a lovely symmetry. The slope of this line relative to the horizontal is the same as the slope of this line relative to the vertical. So let's redraw it. Let's just abstract out of it. We have your coordinates x and t, and we have my coordinates t prime and x prime. A light signal, let's put a light signal in there. A light signal moving to the right is at 45 degrees, and a light signal moving to the left is at 135 degrees. So you see what's happened. The new coordinates are sort of symmetric relative to the light ray here, but the surface, which is the surface of simultaneity, let's give it a name. This is the surface of simultaneity in the moving reference frame. The set of points that the moving observer says are all at the same time are tilted relative to the surface of simultaneity in the rest frame. And they're tilted exactly the same way that, that the time axis is tilted. So it's a very simple construction. Now, from this construction, we can make some guesses. Not guesses, we can actually derive the form of the Lorentz transformations. Let's work out the Lorentz transformations. We know a good deal about the relation between xt and x prime and t prime. We know a good deal, but we don't know everything. So we need some more input. Let's go back to Galileo. Galileo said x prime is equal to x minus vt. All this says is that when x is equal to vt, x prime is equal to 0. But that should be true. That should continue to be true. It should be continue to be true that, as far as you're concerned, my position satisfies x equals vt. So when x is equal to vt, you're talking about my origin of coordinates. So it must still be true, not that x prime is equal to x minus vt, but that when x is equal to vt, x prime must be 0. My center of coordinates is what you call x equals vt. That continues to be true. That's just a statement that this line is x equals vt. And this line, of course, is also x prime equals 0. It's also x prime equals 0. It's the center of coordinates of the moving primed observer. So this equation may be wrong, but it must be correct that when x equals vt, x prime is equal to 0. How could this be wrong, but still be true that when x is equal to vt, x prime is equal to 0? There's only one way. That there could be some factor in here. Let's call it f. And that factor could depend on velocity. That's a possibility. This is still consistent with the statement that when x is equal to vt, x prime is equal to 0, but it's not quite the same as saying x prime is equal to x minus vt. It's a little different than what Galileo would have written, depending on what f of v is here. All right? So this is about all you can do with the equation, with Galileo's first equation. that still allows x prime to be 0 when x is equal to vt, to have some numerical multiple there. And that numerical multiple could, in principle, depend on the velocity. Right? And as I said, all this is telling us here is that x equals vt is the same as x prime equals 0. Now, let's look at this second curve. The second curve over here is t prime equals 0. Why is it t prime equals 0? Because all along this curve here, the primed observer, the moving observer, says that the time is the same. All right, if we just choose it at this point to be 0 here, then t prime is equal to 0 all along this curve. So what it says, whatever the equation for t prime is, it must have the form t minus vx, possibly times some other function of velocity. What does this mean? Why am I saying this? All this says is that when t equals vx, that's this curve, t prime is equal to 0. When t equals vx, t prime is equal to 0. This is about all that you could have and still be consistent with saying that this is the axis x prime equals 0, and this is the axis t prime is equal to 0. So Einstein wrote this down. But one more step. This is not quite enough because we don't know what this f and this g are. They could be anything. They could be anything. These two equations here tell us about the tilt of these axes, but they don't tell us what f and g are. We need one more step. I'll tell you what the one more step is. The one more step is that whatever the equations that you use to convey to me information should be essentially exactly the same as the equations I would use to convey information back to you, with one exception: the sign of the velocity. The sign of the velocity. In other words, if we were to solve these equations for x and t in terms of x prime and t prime, the equations should have exactly the same form, except the sign of the velocity should change. So let's do that. Let's solve these equations for x and t in terms of x prime and t prime. This is the inverse relation. If this is what the moving coordinates are in terms of the stationary coordinates, then if we solve it for x and t, we'll know what the stationary coordinates are in terms of the moving coordinates. And the pattern should be essentially exactly the same. Right? If you see me moving with velocity v, then I see you moving in the opposite direction with velocity v. And the only difference in the relationship would be the sign of the velocity. All right, so I'm going to solve these equations. Let's see. This is a nuisance. It's very straightforward, but let's do it anyway. No, let's prove something first. Let's first prove that f and g have to be the same. Why do f and g have to be the same? That is the statement that everybody agrees about the speed of light. In other words, if one observer calls this line x equals t, the other observer must call it x prime equals t prime. If one observer says the speed of light is 1, that means x equals t, the other observer must also say that the speed of light is 1. That was Einstein's basic principle, that we all agree about the speed of light. If a light ray satisfies x equals t, it must also satisfy x prime equals t prime. Let's see if we can see what that says. If x equals t along a light ray, then x prime here is just equal to t times 1 minus v over f of v. I've just used that x is equal to t. On the other hand, t prime is equal to t times 1 minus v over g of v. I've again just used that x is equal to t along the light ray. So along the light ray, x prime is given by this, t prime is given by this, but it must also be true that x prime must equal t prime. Otherwise, the speed of light would not be the same in the two frames. Well, if x prime must be equal to t prime, it means f and g have to be the same function. No choice about it. So Einstein's assumption that the speed of light is the same in all reference frames required that f and g are the same. So we've learned a little more. Again, we've used the idea of simultaneity as being defined by light rays coming from the left and the right and hooking up at the same instant of time for the observer halfway in between. That told us what this curve was. All right? And now we've used the statement that the speed of light is the same in all reference frames. In other words, if x equals t along here, then x prime must equal t prime, and that tells us that this function is the same as this function. Not quite everything we need to know. We still don't know what f of v is. F of v in the denominator, good. And f is just some unknown function of v that maybe we'll find some reason to set equal to something particular. There must be some rule which tells us what it is. All right, let's now solve for x and t in terms of x prime and t prime. Let's just solve these relationships. Okay, let's do it. Let me multiply this by f of v. F of v times x prime is equal to x minus vt. And f of v times t prime is equal to t minus vx. All right, let's see. What shall we do with these two? I want to solve for x in terms of the prime variables. So let's solve for x in terms of the prime variables. And the best way to do that is to divide this equation by v. Let's see. Let's multiply this equation by v here. Why did I do that? I did that so that if I just subtract them, I'll get rid of the vt, and I'll have an equation for x. Okay, let's see what it says. Add them. So I get x times 1 minus v squared on the right. The vt's cancel, and that's equal to f of v x prime plus v f of v t prime. Let me just write that a little nicer. F of v times, I think it was just
X prime plus vt.
x prime plus vt prime. And now divide it by 1 minus v squared. That's the equation for x. There's another equation for t, which is very similar. The equation for t looks very similar. It looks like f of v divided by 1 minus v squared times t prime plus vx prime. That's the inverse relationship. If you go from x to x prime through one set of equations, then the way that you go back is with this set of equations. Well, you would expect, if there is nice symmetry between the two frames of reference, that the two sets of equations should look very parallel to each other. In fact, x and t should be related to x prime and t prime in exactly the same way that x prime and t prime are related to x and t, with one exception, with the exception that the sign of the velocity should be opposite. Well, that doesn't look so bad. Here we have x prime is x minus vt times something. Here we have x is equal to x prime plus vt prime times something. If the somethings were the same, if f of v over 1 minus v squared were the same as 1 over v, the relationship would be completely reciprocal. The relationship would be completely reciprocal. Same here. The relation between the primed and unprimed variables, when you invert it, simply involves changing the sign of the velocity from t minus vx to t prime plus vx. That will be true if f of v divided by 1 minus v squared is the same as 1 over f of v. So far, I haven't told you what f of v is. Now I'm telling you, it's the thing which satisfies this equation. Or another way to write it is that f of v is equal to the square root of 1 minus v squared. Multiply by f of v on both sides. That squares this. Multiply by 1 minus v squared, and take the square root. What was this? What did I do? What I did was simply to make sure that the relation between the primed and the unprimed coordinates were reciprocal. That if the unprimed observer tells the primed observer that his coordinates are related, that the coordinates are related in a certain way, the inverse relationship should be of exactly the same form, except with the velocity having the opposite sign. All that says is if you see me move with velocity v, I see you move with velocity minus v. So now we have the complete set of relationships between the coordinates of a point of space-time in one frame and the coordinates in another frame. And here they are. X prime is equal to x minus vt divided by square root of 1 minus v squared, and t prime is equal to t minus vx over square root of 1 minus v squared. We can solve them. I just did it, but let me write down what the solution is. Solving it meaning to write the equations for t and x instead of x prime and t prime. The inverse relations are x is equal to x prime plus vt prime divided by square root of 1 minus v squared, and t is equal to t prime plus vx prime over square root of 1 minus v squared. Why does one have a plus v and the other have a minus v? For exactly the reasons that I said. One velocity is the opposite of the other. You see me with one velocity, I see you with the other velocity. These are the relationships between the coordinates of two reference frames which ensure that everybody sees the same velocity of light, that light has the same velocity to everybody, and that the relationships between coordinates are reciprocal. Everybody know what I mean by reciprocal? That they have the same form no matter which way you go, from one side to the other. And they're quite unique. That's it. And the new thing here, the new bizarre thing, is that time is not just time. That what's synchronous in one frame of reference, in other words, t equals a constant, is not the same as t prime equals a constant. That's the new thing, that synchronicity is not the same in both reference frames. Now, I've left out the speed of light. By now, I should put back the speed of light, c not equal to 1. And all we have to do then is to put c in to make the equations have dimensional consistency. X and vt have the same dimensions. And in fact, they have the same dimensions as x prime. X prime, x, and vt all have the same dimensions. Well, The only thing that's out of kilter here is that velocity does not have the same dimensions as 1. You cannot subtract the thing with one set of dimensions from a thing with another set of dimensions. 1 has no dimensions, it's dimensionless. Velocity is length over time. All we have to do to fix this is divide v squared by c squared. 1 minus v squared over c squared. If c is set equal to 1, then it just reproduces the original answer. If c is not equal to 1, it's dimensionally consistent. What about this equation here, though? This one is a little bit tougher. T and Vx do not have the same units. T prime and T have the same units, but Vx does not have the units of time. We have to divide this by the square of the speed of light, c squared, and again put c squared down here. So it's T minus V over c squared x divided by square root of 1 minus v squared over c squared. Now it's interesting to look at it. What happens when the speed of light gets huge? The speed of light in ordinary units is huge. That means that this is negligible in the usual situations. Usual situations where the speed of light is 10 to the 8th or 3 times 10 to the 8th meters per second. The square of the speed of light is 3 times 3 is 9, 10 times 10 to the 17th. This is a huge number in the denominator. So for almost all circumstances, this is negligible. Also, v squared over c squared is also negligible. The velocity of an ordinary object is very much smaller than the speed of light. So this practically reads t prime is equal to t, Galileo's equation. It only begins to fail when the velocity gets up near the speed of light. So only when the relative velocities of the observers are near the speed of light does this differ appreciably from Galileo's t prime equals t. Same thing here. When the velocity is much smaller than c, you can ignore this. And it's just good old x prime is equal to x minus vt. It's only when velocities are near the speed of light that the corrections from relativity become important. But they're especially important for light, which does move with the speed of light. Yeah, let's see if we can see from these equations just directly that a light ray moves with the same velocity in either reference frame. Well, we already did it, but let's just do it again. Yeah, let's do it here. If x is equal to t, a light ray satisfies x equals t. If x equals t, this just becomes 1 minus v times t divided by square root of 1 minus v squared over c squared. That's x prime. What about t prime? T prime, again, x is equal to t. T prime is t minus, I think I'm making a mistake. I can't both have x equal t and have the speed of light not equal to 1. I think I want x equals ct here. Yeah, x equals ct. So this is c minus v. C minus vt over the square root of 1 minus v squared over c squared. And this is t prime. T prime is equal to t minus v over c squared times x, which is ct. So that's ct divided by square root, which is equal to t times 1 minus v over c divided by square root. All right, so x prime is this, t prime is this. What is x prime over t prime? Oh God, I hope it works out. No, it should be c. It should be c. Let's multiply and divide by c here. C minus v over c. Okay, yeah, it is. C minus v times t over square root of 1 minus v squared. But we have an extra factor of c downstairs. So c prime or x prime is equal to c t prime whenever x is equal to ct. Magic. The speed of light is the same in all reference frames with this transformation. The end product here is the important thing. You can now test this out. Oh, what about, okay, if x equals ct, we've just proved that x prime is equal to ct prime. A little exercise is to show that if x equals minus ct, that's a light ray going in the other direction, that x prime is equal to minus ct prime. That's something else you can check from this. It's also true. So that means a light ray going in either direction will move with the speed of light in either of the two frames. Okay. What's special about these transformations? Namely, that light moves with the same velocity in either frame, and the relationship between the two sets of coordinates is reciprocal, has exactly the same form, except with the velocity having changed sign. That's what's special about them. And these, of course, are the Lorentz transformations. These were not the way that Lorentz derived them. In fact, I don't even know that Lorentz did derive them. So that's special relativity, or at least the portion of special relativity that has to do with the xt coordinates. I think we're about finished now. What I was going to do, which we will do next time, is to derive the contraction of lengths, the dilation of time, and some various special relativity effects, dilation of time being the most interesting one, and then move on to more about the kinematics of special relativity, what proper time is, what momentum is, what energy is, and so forth. Any questions thus far about what we've done up to now?
And our next class is at 6 o'clock on the
6 o'clock. 6 o'clock, yeah. Any questions about the physics, though?
Yeah.
Yeah.
Going back to your initial, when we first jumped in, you said if you were moving by the gentleman in the middle at the time that the two flash were
Yeah.
at the same time, if you were in the middle when the two flashes got to the middle, you'd see them at the same time.
Right.
But you see this one is having traveled farther than this one. Is that correct? If you're zipping by the...
Yeah, what you're saying, okay. The thing to do is to draw a picture. You're saying, forget this guy over here. Let's talk about somebody else who happens to pass through this point over here. He's moving, but he sees the two flashes of light at the same instant of time. Right? That's what you're talking about. But he's not midway between the two observers. He doesn't satisfy the criterion that he's midway between the two observers.
He sees this one as having traveled farther
Yeah,
than that one.
right. Right. So there's no reason for him over here to say these two flashes were at the same instant. He sees the light get to him at the same instant, but he's not midway between them. So again, he will not call this point simultaneously. This is the point which is midway between them, and this is the test point for deciding simultaneity from the moving frame.
They'll get to him at the same time.
Yeah.
People say they were emitted at different times.
Right, 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 right. Because after all, this one is further away from him than that one. Right. Good. This is a nice construction to go through. It's not very hard. All you do is you take x equals t, which is the light ray. You say it passes through the point x equals vt plus L, and then work your way backward with a backward light moving, a backward light ray until it hits the point x equals vt plus 2L, and that tells you exactly where this point is. It tells you what counts as simultaneous in the moving reference frame. That's the key, or at least that's half the key. That's half the key to the Lorentz transformation. The other half is the statement that the relationships between the two frames should be symmetrical, apart from the change of sign of velocity. Those are the two key ingredients that Einstein used. In one form or another, these were the equations, these were the principles that he used, and no other, to get to this point. Okay, so if we're finished, we'll move on next time.
The preceding program is copyrighted by Stanford University. Please visit us at stanford.edu.